In this video, we're going to talk about what exactly is a differential equation. So, very simply, a differential equation is any equation that involves a derivative. Okay, but more specifically, it's any equation that connects a derivative of a quantity with the quantity itself. And also possibly the time, the independent variable t, can also be involved, but it doesn't have to be. So here you go. Here's an example. We have some quantity y, and suppose I tell you that dy dt equals t times y squared. There you go. That's a differential equation. Okay, so what we're saying is there's this quantity y that's changing, and how fast it's changing, right? The rate of change at all times is equal to whatever the time is times whatever y itself is squared. So for some reason, for whatever reason, this quantity changes in that way. It's how fast it changes is always going to be equal to what it's equal to squared times the time. Okay, so that's a differential equation. Another example, dy dt equals 4y. This one's a little bit simpler. This one does not involve the independent variable t. This just simply says that the quantity y changes at a rate that is always going to be equal to just 4 times whatever the number itself is. Right? So if at any given time y is equal to 3, then the derivative would be 12. Y would be growing at a rate of 12. If y is 7, it will be growing at a rate of 28, and so on. So this differential equation sort of describes how y grows and sort of expresses the fact that how fast y grows depends on what y actually is, how big y itself is. Okay, now the first thing I want to say about this, and it's the biggest mistake that students make at first when they learn about differential equations, is that differential equations are not explicit formulas for the derivative in the way we usually mean that. So in other words, here's what I mean by an explicit formula. dy dt equals 4t. So I want to really point out that that and that are different, or saying different things. This one's a differential equation. This one is just a formula for the derivative. When I say explicit formula, I mean only involving t. If we had this, we would know what the derivative is at any time, right? Just you tell me the time, I'll plug it in here, and we'll know what the derivative is. See, the differential equation does not work that way. This doesn't tell you what the derivative is at any time. It tells you what the derivative is if you happen to know what it is, right? So it's a connection between the derivative and the quantity itself, not just a straight up formula involving time. These you deal with in Calc 1. These are differential equations. Okay, so now we take this a step further. And the next thing is called an initial value problem. And that's where you tie together a differential equation, say dy dt equals t times y squared. And you also say what y is at one point. Say y of 0 equals 1, for example. Okay, so the idea is this. A differential equation on its own is not complete information. Right? A differential equation gives you a way to get at the derivative. The derivative is how the quantity changes. But how it changes is not the same. You can't just based on that tell what the quantity will be at all times. You actually have to know where the quantity starts, so to speak. And so that's what the initial condition is. It tells you, all right, well, y at the beginning at time 0 is equal to 1. Okay, now and then the differential equation sort of takes over from there and describes how y will change from that point. I always liken it to if you give somebody directions to your house, right? The directions may be go 2 miles, turn left, go 3 miles from there, turn right, etc. But the directions only make sense if you know where you begin, right? You have to ask the person who's trying to get to your house, well, where are you starting from? That's the initial condition, right? If you follow the same directions, the differential equation is like the directions. If you follow the same directions but from a different starting point, of course you're going to end up somewhere different. So the differential equations are just the directions. It just tells you how it grows, how it decreases, etc. But the context of that is where does it start? And then between the two of them, you, in theory, can predict where y will be at any given time in the future. So an initial value problem is a combination of the pure differential equation and the initial condition. So we could have the same differential equation with a different initial condition, and we will get a different answer when we learn how to do these. So same differential equation, but maybe now we'll start at 0. Y of 0 equals 0. Okay. Now, let's talk about what we're going to do with these. When you have an initial value problem, your goal is to describe the quantity, the y, right, as a formula if possible, otherwise qualitatively or numerically. So remember we talked about how any quantity that changes, you have 3 ways of describing it. A formula if you're lucky, and that's the best. But if you're not as lucky to have a formula, you would describe it quantitatively, meaning words and graphs, or numerically, meaning a table of numbers. So that's going to be our goal. We're going to start with a differential equation and an initial condition, and our goal is to describe y in one of those 3 ways. We'll try to get a formula if we can, but you'll see that that's not always possible. We'll consider ourselves lucky if we can get a formula, and then we'll fall back on just trying to get a graph of it and trying to come up with some numbers. And so that process is called solving the initial value problem. Now, I'm not going to talk about how to solve it right now, but what I want to just, that's what the whole course is about, but what I want to do right now is just sort of show you what the answer might look like. And I'll give you some examples. The examples I've already started for you we'll be able to write the answer down as a formula. It'll be the best case scenario. So let me go back to that one that I just wrote down. The differential equation was that the derivative was equal to the time times the quantity squared, and the initial condition was y of 0 equals 1. Now, keeping in mind that I'm not showing you how I got this solution, but let me write down the answer. And it's going to be a formula answer. And it's going to be that y equals 2 over 2 minus t squared. I claim that that is the answer to that initial value problem. Now, again, I have not shown you how I got that. That's going to come later. But at this point, what I want you to see is that it is the right answer. Can you check that answer? So that means 2 things. That means, first of all, it has to satisfy the initial condition. So when we plug in 0, do we get 1? Yeah, that's easy to see, right? You'll get 2 over 2, which is 1. Check. All right, but then the more interesting thing is, does it actually obey the differential equation? And remember, the differential equation says that its derivative is t times the thing squared. Well, let's check that out. So the derivative, let's see if we can work this out. Okay, so let me rewrite this as 2 times 2 minus t squared to the minus 1. The numerator here is just a number, so I don't have to get into the whole quotient rule to take its derivative. I can just do it like this. So let's see. So if I take the derivative, that'll be negative 2 times 2 minus t squared to the minus 2. And then there's a chain rule piece. I have to multiply by minus 2t. Okay, so I think when I write that up nicely, that'll be a positive 4t over 2 minus t squared squared, right? The negative 2 power means it's in the denominator squared. Okay, so that's the derivative of this candidate answer, right? That's the derivative of my y. That's this side of the differential equation. Now let me see what the right side of the differential equation is. So t times y squared. So that's t times, and again, my y is 2 over 2 minus t squared, and then it's all supposed to be squared. And does this give me the same thing? I think it does, right? So we'll have a 2 squared is 4. we have this t, 4t, and then we have 2 minus t squared squared. So these two things are equal. The derivative of the y and t times the y squared are both 4t over t minus t squared squared. They are both equal to each other. So this differential equation has been satisfied. Okay, so my answer, my proposed answer, we can see it works. So that's what it looks like. That's a case where you were given an initial value problem, and we came up with a formula, and we just checked that it works. Again, I'm stressing again, I haven't shown you how I got that answer, but the thing to focus on now is that we can check whether or not it works. Okay, let me just give you another example. Suppose I gave you that other one I mentioned, dy dt equals 4y, and suppose the initial condition is 3. So I claim that a solution, and again it's going to be a formula solution, we're going to be able to actually write the answer down as a formula, is that it will be 3e to the 4t. Nice exponential formula. So first of all, can you see that when you plug in 0 you will get 3? Sure, because e to the 0 is 1, so you'll get 3. Okay. Now, this one will be a little bit quicker. dy dt, the derivative is, it'll be 3 e to the 4t, and then chain rule, right? Derivative of 4t is 4. So 12 e to the 4t. And then the other side of the differential equation is 4y. So the derivative is supposed to be the same as 4y. So that's 4 times 3 e to the 4t. Yep, 12 e to the 4t. Yeah, so you can see, yeah, they clearly match up. That is the right formula. Okay, now, again, I want to stress that point I made earlier, that dy dt equals 4y is not the same as dy dt equals 4t. That is a different expression for the derivative. This is an explicit formula for the derivative, and you learn in Calc 1 how to figure out the formula here, right? The formula would be you do an antiderivative, so it would be 2t squared plus c, and I'm going to use the same initial condition. I'll just rewrite it. Y of 0 equals 3. You can use that to figure out what the c is. So when you plug in 0 for t, you're supposed to get 3 as an answer. So we get 3 equals 0 plus c. So we get c equals 3. So the answer would be y equals 2t squared plus 3. So you already know how to solve those. When you have an explicit formula, you take the antiderivative. We know taking the antiderivative can be hard, and there's lots of them that we can't do, but if you can do it, that's how you do it. So you see, very different kind of formula here than we got up here. This is an exponential up here for the dy dt equals 4y. This is just a quadratic. This would just be a parabola for dy dt equals 4t. Two very different situations. Okay, and now I just want to mention the big picture, sort of the whole process that differential equations are a part of, is that you start with some real-world situation, and the first thing you do is you have to turn that into a differential equation. So that's called modeling. And we will talk about that in this course as well, right from the beginning. You know, it's one thing if somebody hands you a differential equation that you can analyze it and come up with solutions. That's great. But what is that differential equation? Where did it come from in the first place? What real-world situation is it referring to? Right? So, these quantities that I keep talking about, they will be representing something in the real world, whether it be the location of a moving object or the temperature of something or anything that changes over time, right? And somebody has to get that first differential equation. Somebody has to figure out what differential equation it is that governs how this thing changes. So that's called modeling, and that's as important as anything else in this course. But then, of course, the second part is once you have the differential equation, trying to solve it. And again, that will be analytically if possible, in other words, coming up with a formula, or qualitatively, coming up with a graph, or numerically, coming up with a table of numbers. Now I do want to just throw something in to show you the difference between the three approaches. Suppose I gave you a differential equation dy dt equals square root of y minus t squared. And suppose the initial condition is that y starts at 2. Okay, this differential equation, I don't know that I could solve it in terms of coming up with a formula. I don't know that I could give an analytic solution to this. So, as far as a formula goes, I don't know. I haven't given it too much thought, but this would be, I think this would be very tough, if not impossible, to solve. So I'll just put question mark. I don't know. Maybe somebody could solve it, but so we're going to run into these a lot. We're going to run into differential equations where we can't come up with a formula that works this way, right? Where if you took the derivative, it would be the same as if you took its square root and then subtracted t squared. I can't think of a formula that works that way. That seems really tough. But that's where the other two approaches come in, the graphical and the numerical. Sorry, the qualitative, which includes graphical, and the numerical. And so and I won't really be able to prove to you that this is the right answer, but let me just show you. This is what your answer would look like in those cases. We could do a graphical approach, and I'll just tell you that this a formula that follows this differential equation and starts at 2, so this is your y-axis, this is your t-axis. It turns out that through methods that you will learn, it will do something like this. It will go up, then at a certain point it'll turn around, and then it'll drop. So, although we don't know the formula, we know what it looks like. And that's nice, and that's, like I said, that's qualitative. That gives us a general sense of the behavior of y. Y initially increases, but then it's sort of, it maxes out at some number, and then it starts dropping, and then it goes negative, and it keeps dropping. So in words, that's what y will do. But we can also do, through methods you will eventually learn, a numerical solution. So that's where we'll just grind out actual numbers for t and for y. And I've done this, and again, you will learn how to do this in a second, but I'm just trying to show you what answers would look like. Well, we know y starts at 2, and it turns out that if y follows this differential equation, then it will be at approximately 2.73 after half a second, 3.31, 3.44, 2.79, and so on. I'll just stop there. So that's what a numerical solution to this initial value problem would look like. So when you can't get a formula solution, you will still be able to at least get a picture, a graphical solution. There's more to qualitative than just graphical, but I just thought I'd show you that right now. And you can get a numerical solution. So, all right. And again, that's your sort of two backup approaches when you can't solve it analytically, which is very often. Okay.